Hi, today I'm going to cover the inter-process communication through shared memory. So let's walk through some basic concepts first. What is inter-process communication? So IPC is only useful for those processes that have requirements of data sharing and message passing. For those processes, they are called cooperating process. For the rest of them, they are called independent process. IPC, by the definition, is simply the data sharing mechanism between different running processes. Notice it is processes, not threads. I also provide some applications here. So the first one is Java RMI. This is a Java API that allows different programs to share a common Java class. And Apple Events is the basic inter-application communication mechanism in macOS. So imagine you're using a text editor in macOS and want to look up files. It will wrap up a data structure that containing the file directory you input, and the kernel will transmit this data structure to the Finder application. The Finder will parse it and do the actual file locating job. And last but not least, we have microkernel OS. This is an application I personally find very interesting, so I got an image here. We have monolithic kernel-based operating system where the kernel is huge. It deals with everything. It deals with device driver, the file system. But here in microkernel-based, the kernel only handles basic IPC, virtual memory, paging, and scheduling. All the other old functions are moved to user mode, and now they are called servers. If a user program want to request any service from the server, like a user want to write into disk or read from disk, it will communicate with file server in user mode directly. So imagine this system will have a lot of IPC going on every second. To summarize it, the more distributed a computer system is, the more IPC we're gonna need. So here are some commonly used IPC approaches. We have pipes. This is something we're all familiar with. And we have FIFO, and we have message passing. Message passing is also worth mentioning because it's used a lot. It's like one process pass a message to kernel, and kernel transmit it to the second process. And we have shared memory. There are also a lot of approaches that are not listed here, like a socket. Yeah, we heard socket a lot, but socket is also one of the IPC approach. And next, what is shared memory? As you can see in this image, simply it is just a policy that makes memory shareable through LLPs. Are they processors or processes? Well, it depends on the context. If we're talking about the hardware, they could be multiple CPUs or just multiple cores. If we're talking about software, it means multiple processes. It's also worth mentioning that the hardware level shared memory feature can affect the OS design of the shared memory IPC. So let's take NUMA as example. NUMA is non-uniform memory access model. So in such an architecture, we have usually more than one memory nodes, and the CPUs are divided as different clusters. Some of them have faster access speed of node A, and some of them has faster access speed to node B. Given by this feature, we want to make our OS aware of the different access speed. Let's say we have 10 child processes forked, and 8 of them is in a cluster closer to node A. Apparently, we want our shared memory to be located within node A. So this is their relationship and how they interact. Please don't get confused. Let's take a look at the memory allocation attachment process. Here, this process is handled by the kernel. So usually one process requests to allocate these shared physical blocks. The kernel deals with this request, and after successful allocation, it returns a unique identifier. Identifier usually is an int number. After the allocation, each process must request to attach before officially using it. Attach means that the kernel map this physical address to somewhere in their virtual memory space. It doesn't have to be the same address number. You can see here process A and B, they have different virtual pages, but they are both mapped to the same shared memory block. Oh, but one limitation is that the virtual memory pages need to be continuous. You cannot say we have enough pages to hold the physical memory, but these pages are located separately. If that's the case, the allocation or the attachment will fail and return like -1. So let's walk through some important Unix system calls to implement the shared memory IPC. The first one is shared memory get function. This function returns you a unique identifier linked to a distinct physical memory block. So about the arguments, the first argument's key is it might be wrong to describe it by unique identifier. It will be confusing, but the key is different than the return value of this function. The key indeed should be unique. If you keep feeding this function a same key, the kernel will not allocate a new block for you. It will simply return to you the same identifier. So the key can be generated by ftoke function, which is something you can see in later slides. Size here is rounded up to a multiple number of page size, the 2 megabytes. But by manipulating the flag here, you can set the default page size to 1 gigabyte. And also the function will create a data structure upon a successful allocation. The data structure is very similar to the inode of file system. You can see it in the next slide. It's a very interesting similarity. And the next function is shmed, the shared memory attach function. This is one that attaches the physical block to each processor's virtual memory space. It returns a pointer. The pointer is the beginning place of the virtual memory space. It indicates like which part of your virtual memory space is mapped to our physical memory. Here, the second argument, you can actually select the beginning address of the beginning virtual address yourself, but if you set it to null, the kernel will decide the first available one for you. And the first argument here, the shared memory ID, is simply just a value returned by the first shared memory get function. So this shared memory control function is the one you can perform different operations depending on this opcode. Some common used opcodes are like ipcstat. So if you use ipcstat, this function will return this data structure created by get function to the buffer you provide here. And if you set the opcode to IPC remove, it will just simply remove the physical block indicated by this shared memory ID. And also we have shared memory deattachment. This simply deattaches the virtual memory to physical memory. Imagine it like the close function in our file system. So this whole stuff looks a little bit like our file system, which is very interesting design similarity. So here's a small code example. You can see here there's a shared data T structure. Imagine it as a structure, whatever you want, whatever you need to pass through different processes. And here we have the key generation. The ftoc function takes a file path and a project ID as input. As long as the combination is different, it will return you a different key number. So here we use share memory get function to create a new physical block and return you the identifier. Then you must use this identifier to attach it to somewhere in your virtual memory block. So you can see this schmat function takes a null pointer, so the shell will choose the virtual memory space for you. So this is something you must be very careful about. Keep in mind that through this method, every process is reading from or writing into a same physical block. Every time you use the schmat function, it will return you a pointer to somewhere in your own virtual memory space, but after mapping, they will all point to the beginning of the real physical memory space. If you want to write a different data structure into this shared memory space, make sure to use a new pointer. This new pointer will point to like somewhere below the original beginning. You can see the example here. Process A used the schmat function to allocate a space for this shared data. And then it creates a pointer pointing to the beginning of the block plus the size of this shared data. And that is a place where it can write into a new int array. And in process B, we can access to the shared data structure and the array process A write into. And below this data structure is the new place. We can write a new integer in it. Just keep in mind using new pointer anytime. So as we all learned from the thread lecture, the resource sharing most times can bring up some risk condition issue. So our shared memory IPC method also needs some synchronization. The way to use mutex and semaphore and conditional variable are not much different than the thread version, so I'll skip them. Just make sure that every time you create the synchronization primitives, create them within the shared memory block. So you can see the example below, the process A and B. A allocate the physical block, and B use share memory get function to obtain the identifier of that block. And below, they both create a semaphore that points to the virtual memory, the beginning of the virtual memory that mapped to this shared block. So when process A writes something into the semaphore, the process B can directly read from it. And you can see the initialization also needs to be done in process A. So here's another situation we need to take care with. Imagine you're running multiple processes in parallel, maybe using the fork function to generate child processes, and maybe one of them is responsible to allocate the shared physical memory using share memory get. There will be a situation that when processes need to use the shared memory, it still haven't been allocated by that specific process because their execution order is totally undetermined. So to solve this problem, we can either use a centralized initialization, and this refers to the similar method we do in the shell implementation. Like let the parent handle the memory allocation and let the child themselves handle the actual execution and memory block attach. So also we can do the availability check, which means you let child process go into a for loop, keep checking whether the block is available. Apparently this is not the best idea. And also we can use semaphore or conditional variable to signal if the parent is, or if the parent or any other process is done with allocation, just signal the rest of them so they know what is the time to keep going. So let's eventually summarize the pros and cons of this method. First, the shared memory IPC is really quick and it doesn't have to do any data copy because other processes are dealing with the same memory block in physical memory. And also it has structure flexibility. You can write any data structure you want into the shared block. As to the disadvantages, as I mentioned before, it will have potential data security issue because if you don't pay attention where you're writing into, you will overwrite the data structure at the beginning of the block. And also there will be potential memory leak. It's the same reason as why we need to use free after malloc. So after we use the shared memory, keep in mind you need to deattach it in every process. And last but not least, we have synchronization overhead because it's based on the shared memory, shared resources, so the synchronization isn't necessary. Okay, that's it. This is my introduction to IPC and shared memory method. So hope you guys find it useful and have a great summer.